Morning.
Hi. Let's see. We have a bit of a technical issue.
And that being?
It's not showing the camera, which is bad.
Oh, that's not good. Where's my...
All right. I might have to quit and restart. Someone in the chat. Yeah, thanks, Dan. Usually it picks it up and does not. So new share content from second camera. That's what this is.
Good morning.
Hi, we're just in the midst of technical troubles. There we go. Now it sees it. All right. Catastrophe averted. Let's see. Where are we? I think there's anything technical stuff going on. I still get a few questions now and then about the quizzes. It's best to ask your TA for details about the quizzes because they handle them. But I guess by now most people have had the quiz in recitation section, so they'll generally be of that format. Okay, wait, there's something else in chat. Let me organize my various windows. Full solutions on homework 2. I can't. They're either today. I think they went up this morning. Actually, at 8 o'clock this morning. Somebody else can check that and tell me if I'm wrong. But okay. Any other administrative things before we get started? All right, partial solutions are available. I thought the full solution should have been up by now. Give me 1 second and I will look. It might be tomorrow morning. I try to make sure people have enough time to work on them without seeing the solutions, but also some time to enough time then to see them before quizzes and things. So I try to kind of balance those two. Let's see, the partial 2 February. Oh yeah, I'm sorry. Right. Today is Thursday. I lost track of the days. Right. They go up Friday at Friday morning, 8 a.m. tomorrow morning. Right. Okay. And the partial solutions are there. And the idea is, I didn't put this on the webpage, but you're supposed to really struggle with the problems for hours and hours until you're, on some of the harder ones, pulling your hair out, and then check the partial solutions if you're stuck. And the partial solutions will sort of just in words tell you what you sort of want to do. And then after that, after a couple more days, then the full solutions will be up. And then you can, so the idea is to give you a hint to get going on anything you're stuck on before seeing the solution. So a bad studying strategy is to just wait and not do the homeworks, and then when the solutions come out, look over the solutions and say, okay, yeah, that makes sense. That tends to lead to problems, leads to trouble when trying to do quizzes or exams or really learning the material, because you have to struggle with it yourself in order to really learn it. Okay. And I'm sorry for the pounding. There are contractors working on the roof of the house right about here. And so at some point, a boot may come through the roof, through the ceiling into me. We'll see. I'll give you something exciting to look forward to. We'll record that. All right, so where we left off, right, we were talking about Gauss's law. And so we're going to just do a couple more things with that. And Gauss's law tells us that the electric flux through a closed surface is equal to the charge enclosed by the surface over epsilon naught. And we know that the electric flux through a closed surface, is integral of E dot dA. So that's equal to Q enclosed over epsilon naught. And we did a couple examples of this. One of the ones we did last time, we said, okay, if you had a line charge of linear charge density lambda, how would you find the electric field a distance d away? And so I don't want to redo that example because we got to move on, right? I'll just remind you, we said, okay, let's try to find the total flux through this wall, the curved walls, and through the ends of the can, right? So you're imagining this Gaussian surface surrounding the wire, and you make it some length L, and the length L will drop out at the end. And so we did that. So we found the total charge enclosed by this. The total charge enclosed in the can would be lambda times L. And we found that the flux through it, integral, if you're looking back at your notes, integral of E dot dA, we said, well, E is the same everywhere on that curved surface, whatever its value is. So Q enclosed was lambda times L, the charge density times however long this can is. And then we said that would be equal to E dot dA would be the total flux through the curved part plus the total flux through the two ends. And for the total flux through the curved part, we said that that would wind up being E times 2 pi d times L, because you have E would, if you remember how we did it, we said E would be the same everywhere on the curved surface, and so would pull out of the integral and would point out. And so E and dA were always parallel. And so you just wound up with E times the surface area of the curved part of the cylinder, which is 2 pi d L. And then we said the flux through the two ends would be 0. And so then we equated this to that. This to Q enclosed over epsilon naught. So then from Gauss's law, we were able to say that E times 2 pi d L was equal to lambda times L over epsilon naught. So the flux through the can, the curved part, and the two ends, and the two ends were nothing. So the flux through the walls is equal to the charge enclosed over epsilon naught. The L's canceled, and that left us with E was equal to lambda over 2 pi epsilon naught d. So if you go twice as far away, if you double d, the electric field gets cut in half. Right? Okay. All right. So after that, we did an infinite sheet of charge. Well, actually, that one we kind of rushed through. Let me redo that one. So let's suppose that this thing. So in this case, what we're doing is this thing has a surface charge density sigma. Charge with density with surface charge density equal to sigma. So sigma coulombs per square meter. So, okay, and you're asked, we want to find out what's the electric field at distance d above this sheet. So I smear uniform surface charge density sigma onto this plane, and it goes out in all directions infinitely far. And there's sigma coulombs per every square meter on the plane. All right, for purposes of doing the problem, let's do this. Let's try to draw it in perspective. All right, so here's our sheet. And then our Gaussian surface, and this is a little tricky to picture. The Gaussian surface is a can that is above the plane, comes down like this, hits the plane, cuts through, continues on like that, and then has an underside like this, and then closes like that. So if you're, so if you look into the camera here, right, this is the, I assume you can see me as well as the video, or as well as the camera. Good. So this is our plane, and returning our high-tech piece of equipment here, lab equipment, right? So the Gaussian surface is this, and then it continues on through the plane and goes underneath. And so the top surface, the top of the surface is this, then it has curved walls there and more curved walls underneath, and then it has the bottom surface. So what we have to do is we need to do two things. We have to figure out, so that is represented in this drawing. So we have to figure out two things. One, what's the total flux through all of the walls of this thing, and how much charge is enclosed in it, right? So integral of, switch colors here, integral of E dot dA over this whole curved surface, that's going to be the flux through the ends plus the flux through the curved part. Now, there's an important thing in doing this. The reason I choose this as my Gaussian surface is important. I don't know what the electric field is at these points. Like, so if this is my surface, I don't know what the electric field is a distance d away from this surface. But what I do know is it's the same here and here and here at all points a distance d away, because this thing's infinitely big. So the integral of E dot dA over the whole surface. So I don't know if this thing has some surface charge density sigma, E is going to point straight up when you're above it and straight down when you're below it. Let's assume this is positive charge. So this will be integral of E dot dA over the two ends plus integral of E dot dA over the curved part. Okay. So if you continue this, integral of E dot dA over the two ends, let's say our can has a radius of little r. And I know we did some of this, we just rushed it last time. So if our soup can or paper towel roll has a radius of r, then that should have a vector. E dot dA on the two ends, E points straight this way. And dA also points straight that way because dA points out from the surface. So E vector dot dA is going to be equal to E, magnitude of E vector, times magnitude of dA vector, which is dA. Cosine of the angle between them is 0, because dA and E will point the same way. So that'll just be E times dA times cosine of 0, which is 1. Plus, and now this part's going to be quick, since the E field is pointing straight away from the plane, there's no electric flux through the curved parts. In the same way, if you imagine, right, if you had that paper towel roll made of screen and you plunged it through here and water were spraying straight up and straight down from this plane, the flow through the curved part of the screen would be nothing, because the water's headed this way and the screen normal on the curved part is headed sideways. So there would be no flux through the curved part. Okay, so now we can continue this. E times dA. E is the same everywhere on this circle and on this circle. And so that's just going to be E times pi r squared times 2, because there's a top and a bottom. All right. Okay, so that's the end of the left-hand side of Gauss's law. So are there questions on this so far? I do not drive a Subaru Forester. Although not that there'd be anything wrong with that. Other than that, I'd be tempted to drive it off a cliff just so that I wouldn't have it anymore. Okay. The ends represent the top and bottom of the cylinder. Yes. Yep. Right. So the cylinder, right, if you're imagining a soup can or whatever, it plunges down through. And if you just picture the water analogy, you've got water spraying up this way and down underneath. And so you really are only getting flux through the flat circle at the top and the flat circle underneath. Okay. All right. Other questions so far? Yeah, I'm sorry, Caitlin. I guess they're fine. I just know, I don't know. There's something about them that bother me. Okay. Good. So now we know the flux through the whole can, and now we just have to find Q enclosed. Q enclosed over epsilon naught. So this is our left-hand side of Gauss's law. This is the right-hand side. Okay, this isn't going to be bad. If we know the thing has a surface charge density of sigma and this can plunges through it, the question of how much charge is enclosed in the can is really just asking how much charge is on this circle here. Well,
actually, I
Q
have a small
enclosed.
question before we move on, if you don't mind.
Yep. Go ahead.
Just looking it over again, just kind of trying to understand it. Now, why do we get 2 pi r from E integral dA?
Integral of E dot dA, you get pi r squared, not 2 pi r.
That's what I'm sorry, 2 pi r squared.
Oh, yeah.
I said that.
So the reason is because, okay, so basically E is the same everywhere on this. So the E field's coming up through this.
I know why E is the constant, but I don't know why dA becomes pi r squared.
Okay. Because, so what happens is now so E is a constant, so you pull it out. And so now what is the sum of that little area plus this one, plus that one, plus that one? It'd just be the area of that.
And that's represented by dA. So it becomes pi r squared, which is the area of the circle.
Exactly right. Yep.
Okay, thank you. That makes more sense now.
And then the 2 is because there's that one plus, don't forget the one on the bottom.
Yeah, I got that. Thank you.
Okay, yeah. What else? Okay, so good. So Q enclosed is just going to be the surface charge density times that area, the area of the circle, because that's how much of the charge on this plane is caught inside the cylinder. So that's going to just be sigma pi r squared, and then we need over epsilon naught. All right. So questions on this? All right, so equating these two, putting these together, we're able to say that 2e times pi r squared is sigma pi r squared over epsilon naught. Pi r squareds cancel, and that tells us that E is equal to sigma over 2 epsilon naught. And again, I know we mentioned this before. If you look at that example we did that I posted the video for, we find the E field above a ring of charge, and then we integrate rings to find a disk, and then we let the radius of the disk get very large, and we wind up with exactly this answer for the electric field above the disk for a large disk, where large means the disk is large, the sheet is large compared to how far away you are from it. So it looks infinite. Right. The ocean looks infinitely big if you're in a boat. If you're 1,000 miles above it, it no longer looks infinitely big. But as long as you're close, your distance above it is small compared to its own size, then that'll be the electric field. Okay, so think about questions on that for a second.
Yeah, how did you get pi squared over epsilon naught again for Q?
Oh, yeah. So this part?
Yeah.
Yeah. So the flux, sorry. From here, I set the two sides equal to each other. And then,
Yeah, what I'm saying is, how did you get Q enclosed though?
oh, okay, right. So let's say, imagine if this were mass, and I told you this thing had a, sigma kilograms per square meter. So if you cut out a square meter, you'd have sigma kilograms. And I tell you instead, you plunge this can through it, and the area that's enclosed is going to be this circle. And so the charge on this circle, because I want the charge inside the can, which is the same thing as saying, what's the charge on that circle? And the charge, because that's the part of the sheet that's inside the Gaussian surface or the can. And so the area of this circle is pi r squared, and the charge per unit area is sigma. So the total charge on that circle is going to be pi r squared times sigma. Is that okay? It's hard for me to tell who asked the question, so yeah. I can't.
So let's say that little circle, right?
Yeah.
Is there any other symmetrical shape that's not a circle?
Yeah. So there's a weird. I didn't want to get into necessarily this with this problem, but you actually don't have to have. In this problem, you could use a Gaussian surface that looks like this, and then comes down that way. So it could have a square cross section. You get the same answer.
Got it. So would the enclosed area now just be a different formula instead of pi squared?
Yeah, that's right. If you use like you had a paper towel roll or whatever, a can that was square on its face and went down through, the only difference is and had a side of length A, like that, and then we're long this way. The only difference is you'd wind up with sigma times a squared here. And for the flux, you'd wind up with 2 times e times a squared here, and the a squareds would cancel out just the same, and you'd still be left with this.
Got it. All right, thank you.
Okay, good. All right, what else? Other things? Okay, let's do couple more. Let's do one more example. Okay, so in this case, we already looked at the case where I just get make good circles about 2/3 of the way around. Then I start noticing, ooh, that's a good looking circle, and then I screw it up at the end. Okay, so let's suppose I have a solid sphere. And we've already done the case, Gauss's law, if you're standing out here. So if I have a solid sphere of radius capital R with total charge Q, then we already know if you're out here, so if your distance, if little r is greater than capital R, we already know that E equals 1 over 4 pi epsilon naught K times the total charge on this Q over R squared. And you can do that with Gauss's law. We did that before, right? You can find that the E field out here just is this. So this whole thing acts like it's a point charge sitting there. You can't tell the difference. The E field here looks the same, whether it's a solid sphere with charge distributed throughout it, or it's a point charge sitting there. In the same way, and we talked about this before, if you're floating out here in space, the Earth's gravitational field on you here is the same whether Earth is a solid sphere, which it is, of mass evenly distributed, or it's all that same mass m all squeezed to a point. It looks exactly the same. But what about, so this is if r is greater than little r is greater than capital R. That is, you're outside. What about little r less than capital R? That is, you're inside. Okay, so now we're asking, what's the electric field here? So now you're at a point that's inside the sphere. And again, we're going to try to use Gauss's law to find the electric field at this point. Now it's kind of tricky, right? Because some of the charge is outside of where you are, some of it is inside. So it's a little harder.
Wait,
So
quick question.
Yeah.
Sorry, what's that above in the E equation? What's that above R squared? Is that Q or sigma?
In the E formula. Yeah.
That's Q. Sorry.
Okay, thank you.
Yeah, total charge Q.
All right, thanks.
All the hammering and pounding is making me get the Bob Dylan song in my head. Rosemary and the Jack of Diamonds and the Queen of Hearts. Right, the drilling kept up in the wall. Okay. Yeah, I'm waiting for the boot. I am too. I'm ready to dive any second now. Okay, so we're going to try to find the electric field here. And so here's the thing you got to think about is you don't know what the electric field here is. If you did, we wouldn't do the problem. That's what we're looking for. You don't know what the E field is here, but you do know that whatever it is here, it's the same at all points on a spherical shell. If here's our solid sphere, if you imagine a spherical shell inside, whatever the E field is here, it's the same everywhere on that spherical shell. Just like you did that first water problem, when you pour a gallon of water here and you want to know, I don't know how much water crosses this little line, but I know it's the same amount that crosses all the little lines that make up an even circle around the point where the water hits the table. All right. No, different song, Eric.
Darn it, thought I was smart. Oh well.
No, I'm not. Okay, so what we're going to have to do is find, so I know the E, whatever it is the same everywhere on this circle or on this spherical shell in blue, but I don't know what it is. So let's use Gauss's law. And what that tells us is E dot dA is Q enclosed over epsilon naught. It's always true for any surface I draw. It would also be true for any crazy non-spherical shell I would draw here too. It's just in that case, it wouldn't really help me solve the problem. It wouldn't help me find what E actually is. Okay, so let's look at the left-hand side first. Integral E dot dA, integrated over this whole spherical shell. E is going to point out or in. It doesn't, you can guess either one. Let's just guess out. We're just going to find the magnitude of it. And it's going to be the same everywhere on this spherical shell. And if E points this way, and we also know dA for this spherical shell also points out. So again, E and dA are in perfect alignment everywhere on the shell. And so again, this turns into E times dA times cosine of 0, which is 1. And even though I don't know the value of E on the shell, I know it's the same everywhere, so I can pull it out of the integral, which leaves me with E times the integral over this closed surface of dA, which is equal to the integral of dA over this closed surface is 4 pi r squared. The little radius, not capital R. All right, so questions so far? Okay, so now let's look for Q enclosed over epsilon naught. So we need the right-hand side of Gauss's law. Then we'll do what we always do. We'll set these equal to each other and solve for E. All right, so this one you got to think about a little bit. How much charge is inside this thing? I have a sphere of radius capital R that has total charge Q, and now I'm asking how much of the charge is inside a sphere of radius little r, where little r is less than. It's the same thing as saying, I have a big sphere of mass M, and then and radius r, and I carve out a section of radius little r, and I hand it to you, and I say, what's the mass of this? it's clearly got to be less. The charge inside the blue spherical shell is obviously not Q, right? Okay, so it's going to be something less than Q. And if you think about it for a second, it's going to be the ratio of the volume, the fraction of the volume that's inside here times Q, right? It's not half, it's not a third. It's going to be Q enclosed is going to be 4/3 pi little r cubed over 4/3 pi capital R cubed. So this is Q enclosed over epsilon naught. Everyone okay so far?
How did you get the 4/3?
Yeah.
That's just the volume of this sphere. The volume inside the blue spherical, the blue dotted line is 4/3 pi r cubed because it's just the volume of this sphere. Right. So just from knowing the volume of a sphere.
Oh, okay.
And then
Is
the
it-
volume inside the whole thing is 4/3 pi capital R cubed.
So Q is like the density, and Q enclosed is like the mass.
No. Q is the total charge on the whole thing.
Okay.
The analogy with mass is I'm just saying, like, look, if you had a sphere of radius capital R and mass m, and I carved out a portion inside it of radius little r and handed it to you and said, what do you guess the mass of this smaller central core of the big sphere is? It's not going to be the full mass because I didn't give you the full thing. I only gave you this central part of it, right? And so the mass of if this were an object of mass, I was just trying to give you an analogy. If this were an object of mass capital M and radius R, and I carved out a central core of radius little r and handed it to you, the mass inside the green spherical shell would be 4/3 pi little r cubed over 4/3 pi capital R cubed, the fraction of the volume I just handed you times the total mass. Okay. Yeah, so you can't use, you can't use surface charge density. It's a chat question. Yes, and the next thing is, right, the 4/3 pi's are going to cancel and leave us with r cubed over r cubed. So this is going to be equal to Q little r cubed over epsilon naught capital R cubed. All right. All right, so think about questions for a second.
Just tripping up on the arithmetic here. How do you end up with big R cubed in the denominator now?
Right, it's just this over that, so this is in the denominator. I mean, right, because you can think about it's this over epsilon naught over 1, flip that over, and so those.
And then you end up, it's like multiplying by the reciprocal, so it's like
Yeah.
multiplying by 1 over E naught, and then you just combine the Q with that, and you'll end up with.
Yep.
Okay.
It almost looks like you integrated in terms of R using the power rule. Is that incorrect to think of it that way? Evan, I'm not sure because I'm not exactly sure what you're thinking of, but it is, I mean, since you're all taking calculus, right, it's no coincidence that, right, the formula for the volume of a sphere is 4/3 pi r cubed. If you take the derivative of this with respect to R, right, take the derivative of that with respect to R, you're going to get 4 pi r squared, right? And so that's so in a way, I mean, you can say if you wanted to find, it would be a much harder way to do it. You could find the total charge enclosed by this by integrating spherical shells from r equals 0 out to little r. And then you'd also find the charge on it, right? Okay. Yeah, for those of you who are forgetting your calculus, be sure to brush up on it. It's the calc in the calc-based physics. Okay. So good. So now at this point, we can just equate these two things, right? The left-hand side and the right-hand side of Gauss's law. If you do that, this tells us that E times 4 pi r squared is equal to Q r cubed over epsilon naught capital R cubed. All right, then the two of those cancel, these cancel two of those, and that leaves us with E equals Q over, QR over 4 pi epsilon naught capital R cubed. Unless I drop terms here. No, I think it's okay.
I had a question about something. If
Yeah.
the 4/3 pi r cubed is the volume, what is the 4 pi r squared for the left?
That's the so 4/3 pi r cubed is that's the volume of a sphere. 4 pi r squared is how much paint it takes to paint the surface of it.
Okay, thank you.
Yeah. Okay, what else? Other things?
Sir, is it good to use constants for surface charge density and volume charge density?
Yeah, you could if you wanted. Instead, I mean, I try to go back and forth so you see examples and problems of both, but you could also say, well, let me ask you this as a side question. Everyone should write this down. I tell you, you have a sphere of radius capital R, a solid sphere that has total charge Q. Just quick, find rho. What's the volume charge density of this thing? Right? I could have told you rho. I could have said I have a solid sphere of charge density rho instead of a solid sphere of total charge Q. Right? But this is a uniformly sphere of radius R and charge Q. So how much charge per unit volume does it have? And take a second, write it down on, even if you have no idea what you're doing, try to write something down for it. I don't know why this is true, but there've been studies that have shown that if somebody asks you I think they're done with math and quantitative sciences. If someone asks you a question and you just try to write something down as an answer, then when you find out the answer, you'll actually remember it better than if you didn't write anything down, even if what you wrote down is completely wrong. So just try. If you don't know what I'm talking about, try to write something down.
Yeah, sir, I think I'm asking you, like, can you put a rho for Q divided by 4 by 3 pi r cube?
Yes. Yeah. So that, and then yes, the short answer is yes, but your question reminded me that I wanted to ask people this. So the charge density is going to be Q over 4/3 pi capital R cubed. So you could do either. So in this answer, you could just substitute. So rho is Q over 4/3 pi r cubed, total charge over total volume. And so for Q, I could just rewrite this as, right, so I can write Q equals 4 rho pi r cubed over 3. And then I could just pick this up and drop it into here and cancel out the 4 pi's if I wanted, and the r cubed. So you can do it that way too. Yes.
That makes sense. Thanks, sir.
Yeah. What else? So questions on doing this in either of these parts? Okay. So we're going to do a couple of things with conductors and just some basic facts about conductors. And then we're going to use Gauss's law to understand them a little more deeply. Together. Okay, so the first thing is, right, what makes a conductor is charges move freely. right? So what makes a conductor is the electrons in the object are free to move. So in a pen, which is an insulator, right, a piece of plastic, there is an insulator. The valence electrons are tightly bound and cannot move. In a conductor, if it were aluminum, right, this thing being aluminum or steel or something, the charges are free to move. And so what that means for us is that has a few impacts in terms of electric fields and potential. Well, we haven't talked about potentials, but we will. Let's start. Let's start with a couple of things. So first, let's talk about inside the bulk of a conductor. Meaning I have a blob of aluminum here. And I want to ask about what happens inside here. So we know that inside here, the charges are free to move around because it's a conductor. And what does that mean for the electric fields in here? First of all, it means that you can't have cannot have E fields inside a conductor. All right, so this is crazy. First, when you hear it, you say, wait a minute, you can't have an electric field inside a conductor? You can't. And I'll give you an intuitive reasoning for it, and then we can do it properly with Gauss's law. Inside the material itself, the intuitive way to think about it is if you put an electric field here, so let's say I put a bunch of positive charges out here and a bunch of negative charges here, you know now there's an electric field that goes this way. So if you're standing here, you'll measure an electric field that goes that way because you'll be able to push away from the plus charges and an E field toward the negative charges, and those vectors will add. So if you're at this point, there's an electric field that goes that way. And you might guess, well, if I'm inside the conductor, I'll still see that same electric field pointing that way. Except the problem is, not the problem, the result of having this electric field is that is going to push electrons and lack of electrons or holes in the presence of the field, and they are going to keep moving until you'll eventually wind up with positive charge on this side of the material and negative charges on this side. Trying to draw this across this whole face. And so you will wind up with an electric field inside the conductor will try to oppose this field, and the net E field inside will be zero. All right, so that's a very sort of hand-waving way of looking at it, and we'll look at it quantitatively in a minute using Gauss's law. But the upshot is the E field will be zero inside the material itself. And then you wonder and you say, well, gosh, how do you know that however I arrange charges out here and out here, how do you know that it'll always exactly cancel to make zero electric field inside? I mean, maybe the charges will move some, but there will still be some electric field in there. And the way to understand it, why it always goes to zero inside the material is this. If there were still a bit of electric field left over inside here, then that electric field would move the charges. And they would keep moving until there are no more net forces on them, because the charges in a conductor are free to move. So they will continue to move until E is equal to zero. So if you have an object that's static and has been in a field for a reasonable amount of time, or reasonable is sort of microseconds, then the electric field inside the material will be zero. Okay, this is actually one of the reasons why, if you can, we can't talk about electromagnetic waves now, but electromagnetic waves are essentially just electric fields and magnetic fields that keep switching directions. So generally speaking, you can't see through a conductor. Right? There are no sheets of aluminum that you can see through because the electromagnetic wave can't pass through the material. It can't pass through the material because the aluminum can't support an electric field at all. In order to see through it, you would have to have the electromagnetic wave pass through it. But right, your windows are insulators. And so you can have an electric field inside the piece of glass. And so the electromagnetic waves can pass through it. You can't pass electromagnetic waves through conductors. It's one of the few accurate things in spy movies when you see they go into these rooms that have these wires going vertically and horizontally. It's something called a Faraday cage. If you try to pass, it doesn't even have to be a solid piece of material. If you have a bunch of wires reasonably close together, it will act like a solid conductor and you won't be able to pass electromagnetic waves through it. So you can't, if you have a room and you don't want any wireless signals to go in or out of it, you just either paint the walls with aluminum or just embed wires in the walls, and the conductors will stop the electromagnetic field from going through. And then how close those wires have to be in order to stop the fields from going through will control what frequencies it can block, in the limit that it's infinitely dense. In other words, smooth aluminum walls, then no frequencies can get through. Right? You can try this. You can try this at home. Take your cell phone. You can go underground, and you'll still, right in the basement, you'll still be able to make a phone call just fine. Take a sheet of aluminum foil, wrap it, connect the call, wrap aluminum foil around your cell phone. As soon as you close the ends, so it's completely encased in aluminum, the call will cut off because you can't pass the waves from your cell phone through the aluminum. Okay. So how do you know? We can see this. We're not going to spend a ton of time on this, but you can also see this in Gauss's law too. You can see why this is true, right? If I have a bulk conductor like this, and I want to know, well, do I really know that the electric field is zero everywhere inside here? So I start with a neutral conductor. If the electric field is zero everywhere inside here, let's suppose, actually, let me switch to one other thing. Let's suppose I actually take this and I put some charge density on it. So let's say I put some excess charge on this block. What we've been doing with insulators, right? We just did this problem. I said you have a sphere and it has uniform charge density and total charge Q spread evenly throughout the volume of this solid sphere. So the question is, can we do the same thing with the conductor? Maybe I take an excess charge Q and I say in this conductor, I take an excess charge Q and I put it uniformly distributed throughout the volume of the cube. We're going to see that Gauss's law tells us that can't happen. You say, well, why not? Well, what I want you to imagine is a Gaussian surface that's inside here. I don't care what shape it is. Maybe it could be a Gaussian spherical shell embedded. This thing is in the center of the cube somewhere. Doesn't have to be perfectly spherical. Doesn't have to be at the center. Doesn't matter. But it's somewhere inside here is this imaginary Gaussian surface. Now, what you know is always true for Gauss's law. The integral of E dot dA over any closed surface is always the charge enclosed by it over epsilon naught. Okay, but the integral of E dot dA over this Gaussian surface is zero. I know it's zero because I know that the electric field everywhere inside the conductor is zero. So if the E field everywhere inside this block is zero, then of course, for any surface I imagine, then the electric the electric field on all parts of that surface is 0. So the integral of E dot dA is always 0. And if the integral of E dot dA is 0, then the charge inside it, the net charge inside it, also has to be 0. So that will be true of any Gaussian surface I make that is inside, completely inside this box, inside this solid cube, rather. And so from that, what I can say is the excess charge is on the surface. So with a conductor, you can't do wait, I've fallen behind on the text chats.
Someone said it can stop microwaves too. Then someone said, "Okay, I'll go put some foil in the microwave," and people are talking
Oh,
about
yeah,
it
yeah,
exploding.
yeah. Oh, so yeah, that's a good. I'm glad somebody asked that. This is why. So if you look at your microwave oven, right, it's why when you look at the door, it's this screen, right? You want to be able to watch for when your coffee is heated up without melting your eyeballs, right? And so the screen hole size is small enough that the microwave, no significant amount of microwave can pass through it. So it's the same thing. That's a metal screen, not a plastic screen. Even if the door is glass, but the screen inside the door is metal.
Although you still probably shouldn't press your nose up against the microwave.
Sorry, what was that?
Although you still probably shouldn't press your nose up against the microwave.
Yeah, it might be best not to, but it's, at least according to general physics, it's perfectly safe. Right. So the walls, what basically happens is the walls of the microwave and the screen will absorb the microwaves. They won't transmit them. It's the same reason you don't put metal in a microwave. It's not going to explode the oven unless you do too much of it. But it will absorb the microwaves, and instead of heating your food, it'll heat the metal. And then I guess the metal will heat the food. They're extreme. Don't do these. Please don't repeat these things. Don't do these at home, but look at YouTube for idiots who have done it themselves, right? Using microwave ovens, you can actually melt steel with a microwave oven if you override the things that cause it to trip off when it uses too much power. You can also electrocute yourself and burn your house down doing it. But if you Google search on YouTube, you can find people who've melted steel. Yeah. All right. Yeah, I'm following. You can melting point of steel is 2000 Fahrenheit. Yeah, you can melt steel with a microwave.
I've done it by conventional means. I don't intend to use a microwave.
Okay, very good. Okay, so the point of all of this is to say that unlike if this is an insulator, you can take a charge Q and put it throughout the volume of the insulator. But if I take a charge Q and say, oh, I have a conductor, and I put a charge Q on it, that charge is only on the outside surface. It will all be on the outside surface, which we can see through Gauss's law. Right? So you can't have excess charge inside a conductor. You can only have it on the surface. You can also show, I don't want to fall behind too much here, which we are a little. You can show that if you have, a thing like this, and inside it, you have basically an empty, like a bubble. The excess charge Q, so this is just empty space. This in here is all aluminum, let's say. And this inside the bubble is empty space. If you put charge Q on this thing, the charge will spread to the outer surface. This doesn't count as a surface. And you can see that with Gauss's law, and your book will show you why. Basically, if you imagine a Gaussian surface around this, the electric field through this Gaussian surface has to be 0 at all points, because the Gaussian surface is in the metal. And that means the electric field is zero in it, which means the charge enclosed by it is zero, which means the excess charge goes to the outside surface, not this doesn't count as an outside surface, right? So if you imagine or think of it a different way, imagine a basketball made of aluminum and you put charge Q on it. You could say, well, maybe this part, the inner wall, also counts as a surface, and some of the charge would be on the inner wall and some would be on the outer wall. And this says no, the inner wall does not count, right? Inside the surface does not count as a surface for where the charge would go. The charge would collect on the outer surface, right? You can, if you want, there's another way of looking at all of this in terms of energy. If I have a block of material and I put a bunch of charge Q on it, a block of conductor, the charge basically wants to all get as far away from each other as possible. And because that would be the lowest energy state. And so that will happen by all the charge racing to the outside wall. It can't do that in the case of an insulator because the charges aren't free to move. So once you pile charges throughout it, that's where they stay. All right. Okay.
Excuse me, sir.
Hang on one second. I see someone has posted a video. Please don't watch the video during class. I know it takes willpower not to watch YouTube during class, but it's best not to. Yeah, Yang?
Yeah. Hi, sir. Please go back to the last. Please see the last two pictures. You mean if the box, I mean the last two one. Yeah, this one and the last one.
Yeah.
Yeah, and I mean, if one box is conductor, you mean in the inside of that box, the electric field is zero, right?
That's right.
But so you mean the surface also is inside part of that box. Also, the electric field is zero too.
Yes. Yes. Yep. So
Okay.
if it's a conductor, if it's an insulator, you can have electric fields inside it. If it's a conductor, you can't have an electric field in it. Conductors don't have electric fields.
Thank you.
Not inside. Okay. All right. So we're going to do one last, and we're going to do this one kind of quickly, and you'll have to do this a little on your own too. We did this problem of I want to do this in class because there's a really subtle point. If I have a block like this, that's a conductor, right? And I say, what is the electric field here? And there's a surface charge density sigma here on this surface. What is the electric field, here at a point just above? And the first thing you want to do is you say, well, we already did this problem. This is like a sheet of charge. And so surface charge density sigma, and you look back at what we got and you say, oh, the electric field, is that me? Oh, all right. And you say, okay, the electric field is sigma over 2 epsilon naught. That's the result we got before. I said you had a sheet of surface charge density sigma, and then we drew a Gaussian. You're looking at it edge on. We drew this as our Gaussian surface, and we found the electric field here was equal to sigma over 2 epsilon naught. All right. So when you go through this in your textbook, there's a confusing thing. When you derive that same Gauss's law for this conductor, you're going to find, okay, you'll draw this same Gaussian surface, goes into the material. I'm trying to draw this like inside the block now and back up. And you try to do the same thing. And what you notice is that in this case, Now you're going to get the flux through the walls. So again, you have integral of E dot dA is Q enclosed over epsilon naught. And let's say this thing again has a radius of R. So here you got to be careful though. So E dot dA this time is going to turn out to be E. And I know I'm rushing this. You're going to have to go through this in the book slowly on your own, right? What we got before was we said, oh, you have flux through this wall and you have flux through this end of the can, both ends of the can. And so we picked up a factor of 2. Here you don't. So when you're reading this in the book and you say, wait, what the hell happened to the 2? In the case of a conductor, you don't have that because there is no electric field inside the conductor itself. And so there's only electric flux through the end of the can that's outside the conductor, not the side that's inside. And so Q enclosed is still going to be equal to sigma times pi r squared. So Q enclosed over epsilon naught is going to be sigma times pi r squared over epsilon naught. And this is exactly the same thing we did in this case, except here we had 2 surfaces that had flux through them. Here we only have 1. And so when you solve this, cancel the pi r squareds, you wind up with E is sigma over epsilon naught. So be very careful when you're reading this in the book. If I have a sheet of charge with surface charge density sigma, the electric field here is sigma over 2 epsilon naught. If I have some big conductor like this, and it has a uniform surface charge density sigma on it, the electric field here is sigma over epsilon naught, not sigma over 2 epsilon naught. So be very careful of where, which problem you're looking at. So a blob of metal, the electric field near it is sigma, the surface charge right near where you're looking, divided by epsilon naught. For a sheet of charge, it's sigma over 2 epsilon naught. Right, can you explain why we don't need the 2 again? The 2 arose in this problem because when you make this as your Gaussian surface, the total flux through it is going to be E times the surface area of that, pi r squared. That's the flux through this end, but there's an end down here too, and there's flux through that because you have an E field going like this and an E field going like that. So then you had 2 times E times pi r squared is the total flux through this can. In this case, if it's a conductor, there is no flux through this end. And so you only wind up with E times pi r squared because there's only flux through this end because there's only an electric field out here. There's no electric fields inside the conductor. And so basically this second part goes to 0, so you don't get the factor of 2. So when you're rereading this in your book, which you really need to, you'll see that sometimes you wind up with a factor of 2, sometimes you don't. So that's the origin of that. So the first example with the 2 doesn't have a conductor that stops the E field from going through it. Yeah, I mean, Dan, that's a subtle point. I mean, there is you still will feel an electric field here. I think the short answer, maybe we can get into this next class depending on time, but I think the short answer for now is yes to your question. I mean, really, it's more complicated than that. It involves, there's still fields from the other charges that are around, but there is also charges move inside here. And so the net result is that if you're near the conductor, it'll be sigma over epsilon naught. If you're near a sheet, it'll be sigma over 2 epsilon naught. Right? Okay, we have to switch gears a little bit just because I don't want us to fall too far behind. So the chapter we're starting is potential, or electric potential. And this is mathematically not super complicated. It's probably less complicated than the stuff we've been doing. But conceptually, it's really a little subtle. So to start this, I want you to remember something from general physics, right? So if I have a mass m1 and a mass m2, I know the force, gravitational force on m2 from m1 is going to be g times m1 times m. Let's say this is the x direction. The force on m1 from m2 is going to be g times m1 times m2 over, if this is a distance, let's say r squared x hat. And if these are ordinary masses, this will be tiny force because g is so small. Okay, so good. And then what you customarily do, if this were Earth or something, if this were a fixed large known constant mass, then what you do instead is you write the force is g m2 over r squared times m1 x hat. And then you say, all right, well, this comes up, this is the same always, right? So this is g times mass. If m2 is Earth, and this is something being pulled by Earth, you just calculate this, and that winds up being little g. So then you say that the force on m1 is just little m1 times g x hat. Okay. Great. So that's a little tour down memory lane from Physics 1. So then what you do is you would say, all right, if I'm above the Earth, then I would say the force on this little mass m, if I call this the y direction, then the force on m is going to be minus mg y hat, or mg times minus y hat, right? Where g you get, again, from g times the mass of this object divided by this distance squared. And what you customarily do is you say, look, for objects near the surface of the Earth, let's just make r be the radius of the Earth. Technically, it's not true, right? If you drop a ball from here to the floor, if you really wanted to be fussy, you would say, well, gravity is getting stronger as the ball is falling because it's getting closer to the center of the Earth. But the height that you drop a ball is small compared to the radius of the Earth. And so you just ignore that and say, look, r is basically radius of the Earth. Of course, if you're launching a rocket, you don't do that because gravity gets significantly weaker as it moves. And so the force on it, you can't just say it's mg. You have to vary g as a function of radius. Okay, so fine. So if you do this, this will connect back to E and M in a minute. You know that this is the force on it. And you also, I hope, remember from Physics 1, although you may not have done it with calculus, the gravitational potential, if you move something from some initial spot I to some final height F, right? You know that VF minus VI is minus the integral of F vector dot ds vector. And if you're not familiar with this, let me just remind you sort of physically why this happens. If you think about it, you can make good common sense out of it, right? You know the potential if I take a mass, I start at I and I lift it, I push it up to spot F, I've done work, right? And the work I've done, you know it's mgh, but let's pretend you don't for a second. What you're really doing is you're saying, look, when I move the mass from here to here, what I'm actually doing is moving it in a bunch of little steps, right? I move it from here to there and there to there. And so I have all these tiny little steps. And in each case, so let's take a look at this step right here. In this step, so if we magnify that, I move the thing a little vector ds. And while I'm moving it this way, there's a force on it. And the force on it is this way. So F and ds are opposite. And if I move this thing, so if I'm asking you how much work do you do in moving a mass, a little step ds vector in a gravitational field that points down, you kind of have an intuitive idea that if I move a mass from here to here over a little step ds vector, and there's a gravitational force down, I don't do any work because I'm just moving a mass across in a gravitational field. So in this case, you already have a feel that you're not doing any work to move the mass along this step. And you already sort of have a feel that you're doing positive work. You actually have to spend energy if you are going to move an object from here to here, if ds, your step points opposite to the direction of the force. And if I move it this way, and my force is down, if I move a mass a little step downward in a gravitational field that's down, I know that I do negative work. In other words, I can get energy back out of dropping this ball the tiny bit from there to there, a little bit of energy. So that is what is encoded here. So of course you have to memorize this, but I want you also to physically understand it. That's really what's encoded in this dot product, right? If F and ds point the same direction, then F dot ds is a positive number. F, right? It's F times ds times cosine of 0, which is 1. And then this negative says, oh, you moved, if your step was in the same direction as the force, you did negative work. And that's why that negative sign is there. If F is opposite to ds, you have to do work to make that happen. Okay? And then it may be, like in the case of you moving something near Earth, that we say, look, this is not very far from, this is about the same distance from the center of the Earth as that is. And so we say all of these steps, during each step, you have to apply about the same amount of force, because we're not going to worry about the fact that gravity is slightly weaker there than it is there. And so in this case, what you do is you say, oh, look, the force on this thing from the move of the mass from there to there is just going to be m times g. And so this, in the case of moving a mass near Earth, force is just mg. And then, so that actually comes out of the integral. And then the force is down and your step is up. And so this negative goes away because if this is in the y hat, if ds vector is ds in the plus y hat, and f is minus mg in the y hat direction, then the dot product of these things is mg times ds, y hat dot y hat is 1. The negative cancels with the negative. And so this thing just becomes the integral from your initial point to your final point of mg times ds. Now that is because we assumed that the force needed to move on each of these steps is the same. And so this just becomes mg times the integral of ds, which is just mg times this distance, which is going to be, right, what you know is the height, how much you lifted the object. All right. Okay, so that is mg times h, and that's the thing you know from general physics. So you know it as, okay, you move an object. What I want you to take from all of this is understanding why this negative has to be there, why that makes sense. And what you know from general physics is you say, look, I move an object from here to here, a height h, the total energy that I have to give it is m times g, the force that it feels, times h, the height that it moves. So you just have mgh. And now what I want you to remember, though, is that it could be if Earth was here and you were moving an object from here to here, now you can't just say how much energy does it take to lift a mass m from here to there, and let's say this distance is h. The work needed does not equal mg times h, because during some of these steps, you do more work than others. So the step from here to here contributes more to the amount of work that you have to do than the step from here to here, because now you're much farther from the center of the Earth. So if this is the case if you're launching a rocket. And so you can't just say it's mgh, because the force on the object is not the same for each of the steps. Okay. Okay, questions so far? Okay, so there's a conceptually subtle thing I want you to think about. And we're going to have to end soon, but this is a really subtle thing. I really urge you to think about it. If I define the surface of the Earth, let's say I define, and you know this from general physics, you can define a 0 point for potential energy. Let's just say I define V equals 0 at sea level on Earth. As soon as I do that, you know, there's some hill here. This spot here, and I know this is not going to seem mathematically complicated, but trust me, you want to mull this idea over a lot between now and Thursday. This spot has a certain number of joules per kilogram associated with it. Okay, how? Well, if I've defined sea level to be V equals 0, it takes a certain number of joules needed to move 1 kilogram from sea level to this spot. All right, so it's a very important idea. As soon as you define a V equals 0, let's say to be sea level on Earth, as soon as you do that, every spot on Earth has a joules per kilogram associated with it. There's a numerical value for, this spot on this spot on my hand, all right, or this spot on the wall. It's the number of joules it would take to grab a 1 kilogram object from the ocean and move it, lifting it all the way up to this spot. And because gravity is conservative force, it doesn't matter how I get to this spot. The number of joules it will take me to move 1 kilogram to here is a fixed value. And then this spot on the wall also has a number of joules per kilogram associated with it. It's a slightly larger number than this one. And so this creates what's called a scalar field. Every spot in space has a number associated with it. This empty spot in space here has a number associated with it. It's the number of joules it takes to move a 1 kilogram object from wherever we've defined 0, and let's say it's the ocean, to this spot. And in fact, all these points here on this sort of flat plane, all these have the same number associated with them as each other. All these spots on this plane have a lower number associated with them. Okay? So it's a very important idea. We're going to find the same thing with electric fields. And I know we're a little behind, so I may do some of this over a video. Right? If I have a charged object here, there is a certain number of joules it takes to move +1 coulomb from infinity into this spot, and that will be what we call the electric potential, joules per coulomb. So study this in your book. That will be the joules per coulomb of this spot in space. And we'll do this more slowly, more carefully on Thursday. And I'll make a video, and you got to study it in your book. All right. Sorry I had to rush at the end, but I at least wanted to get you an introduction. So think about that idea while you're reading the text. All right. And I'll see you. Yeah, cloud recording lectures. Yeah, no, there's no cloud recording of lectures. There's been problems because then people don't show up to lecture once they're recorded. So it's sort of the same. That part is the same as live. You have to come to class. So there is the last page.
Thank you, Professor. Have a good day.
Thank you. You too.
Excuse me, Professor. I have one question about that one. Negative MGH.
Yeah.
Here. Here, the integral f direction times ds direction.